Welcome to the Wonder Fungi Podcast. Today, we are playing Mother Nature.
We really are. And it's funny to think about where we actually are right now, functionally speaking.
Yeah, we're standing right in the heart of our own sterile laboratory.
Exactly. Surrounded by that constant, reassuring hum of the HEPA filters.
And the glow of the climate-controlled fruiting chambers.
Right, and shells upon shells of colonized substrate.
We have spent decades in these lab coats. Decades in front of sterile flow hoods, just obsessing over the microscopic details of fungal life.
And today, we are inviting you directly into this world.
That's right. We are taking you on a deep dive into one of the most critical, nerve-wracking, and frankly magical transitions in all of biology.
It really is a profound transition. We are talking about the exact moment a fungal organism shifts from vegetative colonization to the fruiting phase.
Yes. And if you are a cultivator listening to this, you know exactly what this feels like in your gut.
Oh, absolutely. You've spent weeks meticulously maintaining your sterile technique.
Watching that beautiful, brilliant white mycelium race across your grains.
Or your bulk substrate. It's safe in its sealed container.
But eventually you have to do it.
You have to crack the lid.
You have to introduce fresh air. And we know the anxiety that causes because we have felt it ourselves in our early lab days.
Oh, definitely. You are suddenly exposing this pristine, protected network to the chaotic physics of the open atmosphere.
That anxiety is entirely justified, but, it becomes manageable once you stop guessing.
Right.
Once you start understanding the orchestration of physics and biology that is actually happening at a microscopic level.
I always tell our junior lab techs to frame this entire process in their minds not as following a rigid recipe.
Exactly. It's not baking a cake.
No, it's a manipulation of biophysics. You are orchestrating a massive environmental shift.
So let's start right there, at the climate shift.
Yeah, let's get into it.
When your mycelium is colonizing its substrate inside a sealed jar or a closed tub, it is experiencing what we like to call an underground spring.
I love that term.
It's warm, it's dark, and most importantly, it is swimming in a massive, almost toxic concentration of carbon dioxide.
That high CO2 environment is absolutely essential for the vegetative phase.
Right.
And the sheer scale of it is something most people just don't fully grasp.
Not at all, because in the natural world, standard atmospheric CO2 is around, 400 parts per million?
Roughly 400, yes.
Mm-hmm.
But inside your colonizing jars or your bulk substrate bags, the mycelial metabolism is operating at a breakneck pace.
It is consuming the carbon in the substrate, the grains, the wood, the manure.
And exhaling CO2 as a metabolic waste product.
And because the container is mostly sealed, those CO2 levels don't just gently rise.
They skyrocket. We regularly measure levels reaching 10,000 to 20,000 parts per million inside a colonization bag.
Which is wild to think about.
It is. And in this underground spring state, the fungus is entirely focused on one singular mission.
Horizontal expansion.
Exactly. It wants to consume every available nutrient before a competitor does.
It's like a mold or a bacteria.
Right. It has zero interest in reproducing. It is purely in a state of vegetative conquest.
Hold on, let's clarify something for the listener here, because I know this trips up a lot of beginners.
Good idea.
During this massive expansion phase, you are providing what we call gas exchange, right? Not air exchange.
Yes, that is a vital distinction.
I really want to emphasize that. Gas exchange is the slow, passive percolation of metabolic gases out of a tiny micropore filter patch.
Or just a loosely tightened jar lid?
Exactly. It's just enough to keep the mycelium from literally suffocating on its own waste.
But it maintains that incredibly high CO2 concentration.
Right, and that dense cloud of CO2 is a chemical signal.
It constantly tells the fungus, you are still deep underground.
Keep expanding. Do not expend energy trying to fruit yet because you haven't breached the surface.
Gas exchange is passive. Air exchange is active.
But eventually, full colonization is reached. The substrate is conquered.
The food source is secured.
And this is where you, as the cultivator, step in to play Mother Nature.
You crack the lid.
You introduce a fan. You bring in the ambient light.
You are suddenly subjecting this organism to a massive, simulated, seasonal shift.
You are unilaterally ending the underground spring.
And violently introducing above-ground fall.
And this requires a sudden orchestrated drop in temperature.
The introduction of the light spectrum.
And a massive influx of fresh air exchange, or FAE.
Let's really drill down into FAE. Because if gas exchange is passive, FAE is basically a hurricane.
Fresh air exchange is the active, forceful flushing out of that stale CO2-heavy air.
And its complete replacement with fresh, ambient room air.
This sudden plummet in CO2 levels, dropping from 20,000 down to perhaps 1,000 parts per million or even lower.
That drop is one of the primary physical triggers that screams at the mycelium that it has finally broken through the dense soil layer.
It has reached the open atmosphere.
But what happens if a cultivator is too timid?
Right, what if they crack the lid just a millimeter because they are terrified of introducing contamination?
And that CO2 level doesn't drop enough.
We see the results of that timidity all the time in our environmental extreme tests.
Absolutely. If you attempt to fruit a fully colonized block, but you fail to evacuate that CO2,
And the humidity just sits there stagnant and heavy.
you trigger a biological phenomenon known as overlay.
Overlay is so frustrating.
If you've ever looked at a casing layer and seen a dense, thick, almost crusty mat of mycelium,
Looks more like a white kitchen sponge than a fungal network.
that is overlay. It is a stroma-like mat.
The fungus has essentially suffered a breakdown in its environmental programming.
Because the CO2 remained too high, it stayed locked in its vegetative state,
But because it has run out of new territory to conquer, it just keeps expanding on top of itself,
piling hyphae upon hyphae.
creating a dense, impenetrable, matted barrier that will stubbornly refuse to form a single mushroom pin.
It's basically a state of biological confusion caused by environmental mismanagement.
The fungus is saying, I have no more food, but the air says I'm still underground.
So I'll just keep growing into a thicker and thicker armor.
And to avoid overlay, we have to look incredibly closely at how these indoor controlled environment changes directly mimic nature.
Think about what happens in a forest right before a massive flush of mushrooms.
You rarely see a huge flush in the middle of a hot, stagnant summer day,
You usually have a tropical thunderstorm.
or the sudden, crisp onset of autumn.
We replicate this in the lab with a cold shock.
A sudden drop in ambient temperature by about 2 to 5 degrees Celsius.
And this cold shock isn't just some vague, holistic signal.
No, it is a profound biophysical trigger.
It alters the actual physical properties of the fungal cellular membranes.
Let's look at the cellular architecture for a second. The membrane of a fungal hypha, much like our own cells, is a lipid bilayer.
It's composed of fats.
Exactly.
Right.
When the ambient temperature drops rapidly during that cold shock, those lipids start to become rigid.
Think of butter in a frying pan versus butter in the refrigerator.
Great analogy. The fungal membrane threatens to freeze up, lose its fluidity, and compromise the entire cellular infrastructure.
But I find the organism's response to this absolutely brilliant.
The fungus is incredibly adaptive.
To counteract this cold-induced rigidity, it immediately begins synthesizing and incorporating a higher proportion of unsaturated fatty acids
Specifically, molecules like linoleic acid.
directly into its cell membranes.
The kinked molecular structure of these unsaturated fats acts like antifreeze,
It prevents the lipids from packing tightly together.
which keeps the membrane fluid, flexible, and fully functional even at the newly lowered temperatures.
But here's the magnificent part. That massive biochemical shift in membrane composition isn't just structural.
It acts as a secondary internal alarm bell.
The sudden spike in intracellular linoleic acid tells the organism's genetics the season has definitively changed.
The temperature has dropped. Vegetative growth is over.
It is time to switch to reproduction.
It is a stunning cascade of events where the external physical environment alters the internal cellular chemistry.
Which in turn unlocks the genetic pathways for fruiting body morphogenesis.
And the CO2 threshold we discussed earlier is just as rigid an alarm bell.
I recall a specific series of long-term lab experiments we ran a few years ago.
I remember those. We were testing precise CO2 tolerances in sealed fruiting chambers.
Using those specialized multiple gas detection arrays.
Yeah. We had one chamber perfectly dialed in at 800 parts per million, which is excellent for fruiting.
And another chamber artificially hovering around 1,500 to 2,000 parts per million during the fruiting phase.
The visual difference between the two crops was staggering.
In the high CO2 chamber, we observed a textbook severe case of what cultivators call legging.
Oh, legging is so heartbreaking to witness.
It really is.
For those who haven't seen it, legging is when you get these incredibly long, spindly, fragile stalks.
It just keeps stretching and stretching upward.
But the caps remain tiny, dark, and underdeveloped.
It literally looks like the mushroom is reaching out in desperation.
And practically speaking, it is.
The mushroom is detecting those high levels of CO2.
Which, in a natural forest setting, usually means the fruiting body is still buried under a thick layer of wet, decomposing leaf litter.
Or heavy soil.
So it logically diverts all of its available metabolic energy away from cap development.
And pours it straight into stem elongation.
It is desperately trying to push its cap up into the fresh, oxygen-rich breeze before it opens its gills to release spores.
It's an evolutionary survival mechanism playing out in real time in your tub.
Because if a mushroom opens its gills while still buried under a high CO2 layer of wet leaves,
The spores will just dump into the mud and rot.
the fungus knows this.
So if you are observing your mushrooms stretching out like wet noodles with tiny caps, your CO2 is remaining above that critical 1,000 parts per million threshold.
You don't need more light.
You don't need more water.
You need more active fresh air exchange to sweep that heavy gas away.
Exactly.
So assuming you've done everything right up to this point, you've cracked the lid.
You've dropped the temperature to change those membrane lipids.
You've aggressively flushed out the CO2 so the fungus knows it's above ground.
The climate has officially shifted.
But what is the exact mechanical, physical trigger that actually forces those microscopic hyphae to stop growing in straight lines?
And start knotting together to form the first pins.
To understand that, we have to shift our focus to the second major concept of cultivation.
The evaporation engine and the biological panic response.
Because what we're really talking about here is the mechanics of water.
The mechanics of water are paramount.
Before we get into the physics, there is a foundational biological truth that every cultivator must internalize.
Mushrooms do not fruit casually.
Fruiting is not a leisurely hobby for a fungus.
Nor is it a sign that the fungus is perfectly comfortable and happy.
No, fruiting is a severe biological panic response.
The fungus is throwing massive amounts of precious, stored metabolic energy and structural nutrients into creating a temporary, fleshy structure.
For one singular, desperate purpose, to drop spores and pass on its genetics before it dies.
And the primary environmental trigger for that localized panic.
It is evaporation.
Let's visualize this.
As your mycelium breaches the surface of your casing layer or the top of your bulk substrate block,
It finally contacts that fresh moving room air you just introduced.
almost immediately, moisture begins to physically evaporate off its microscopic cellular surface.
Now, why does this cause panic?
Because to a subterranean fungal network, that evaporation is the ultimate environmental alarm.
It signals to the mycelium that the dark, incredibly moist underground water reservoir it has relied upon for its entire life is exposed.
It is exposed to the chaotic atmosphere and is in imminent danger of drying up entirely.
The organism realizes that the clock is ticking.
The wet season is ending.
It must initiate a reproductive emergency to ensure the survival of its lineage before the substrate turns into a dry brick.
To truly master this, we have to dive deep into the biophysics of this evaporative process.
Which brings us to a concept we use daily in the lab.
Vapor pressure deficit, or VPD.
This is arguably the most critical metric in advanced cultivation. Let's break it down.
When your mycelium is buried deep within the core of a wet substrate,
The relative humidity immediately surrounding those hyphal threads is effectively 100%.
the air in those tiny microscopic pockets between the grains is fully saturated.
In that state, there is absolutely zero net evaporation.
The local air simply cannot hold any more water vapor, so the moisture on the outside of the fungal cells stays put.
But wait, if someone has their fruiting chamber set to 95% humidity, how is evaporation happening?
This is where VPD is so crucial.
When you crack that lid and introduce fresh room air, you dramatically increase the vapor pressure deficit.
You are bringing in air that, relatively speaking, is hungry for moisture.
Even if your room or your chamber is at 95% humidity, that remaining 5% deficit drives a relentless physical engine.
The moving fresh air hits the wet mycelium.
And water molecules are physically and mechanically torn away from the liquid state on the cell wall into the gaseous state in the air.
And the consequences of this are profound.
This evaporation doesn't just dry the surface out.
It creates a massive internal mechanical force known in plant biology as transpiration pull.
But in mycology, we often refer to it as hydraulic redistribution.
Think about the physics of sucking liquid through a straw.
When evaporation pulls water molecules off the exposed tips of the hyphae at the surface of the casing layer, it creates a microscopic negative pressure gradient.
Because water molecules are highly cohesive, they like to stick together.
That negative pressure travels all the way down the intricate branching fungal network.
It acts like a microscopic, organism-wide hydraulic pump.
It physically pulls liquid water, along with all the dissolved nutrients, enzymes, and simple sugars from deep within the protected core of your substrate block.
Rushing it rapidly up to the surface where the reproductive action is initiating.
I love the hydraulic pump analogy because it highlights that this is a highly efficient active transport system.
Driven entirely by the free energy of the atmosphere.
The fungus doesn't have a heart to pump fluids.
It uses the physics of evaporation to do the heavy lifting.
And our lab data shows that the fungal hyphae themselves are not just passive, inert pipes in this process.
No, they act as highly active, localized viper sinks.
We've conducted some incredibly complex laboratory measurements over the years involving a principle called thermodynamic water activity depression.
What we consistently find is that a thriving, pinning fungal patch actively reorganizes the condensation and evaporation fields in the air immediately around itself.
The mechanism there is fascinating,
The cell walls of the fungus are incredibly rich in chitin,
which is a highly hygroscopic material.
meaning it naturally attracts and holds on to water molecules from the surrounding environment.
As the fungus grows, it actually pulls ambient moisture out of the microclimate, depressing the local water activity.
The mycelium is literally shaping the thermodynamic vapor dynamics of the air immediately surrounding its own body.
Which is an evolutionary masterpiece.
The fungus is using the very physics of the atmospheric boundary layer to detect the exact razor-thin line between the damp earth and the open air.
It needs to know precisely where the surface is so it doesn't waste precious energy building a mushroom 2 inches underground.
Where the spores can't escape.
So as the water evaporates off those exposed hyphal tips at the surface, something incredible happens to the internal chemistry of the cell.
Because the water is leaving, but the heavy molecules stay behind.
The signaling molecules, the reproductive enzymes, and the morphogens left inside the tip become highly concentrated.
They hit a critical biochemical threshold.
The concentration gets so dense that it chemically forces the hyphal tips to completely change their behavior.
They stop their linear, exploratory, vegetative growth.
Instead, they begin to branch laterally and literally fuse with their neighboring hyphae.
They knot together into a dense little ball.
This is the birth of the hyphal knot.
This is the very first microscopic stage of a primordium.
It is a profound biochemical shift. But this raises a major structural problem that the fungus have to overcome.
Bridging the gap between the wet, protected environment of the internal cell and the dry, hostile environment of the open air requires a specialized adaptation.
Think about it. How does a single fungal cell, which is basically a microscopic pressurized tube of water, push its way out into the dry, circulating air?
Without its thin walls instantly desiccating, collapsing, and dying.
The answer lies in the specialized secretion of a class of proteins called hydrophobins.
The hydrophobin mechanism is one of my favorite topics in all of cell biology.
It is so elegant. Hydrophobins are tiny, cysteine-rich proteins that the fungus continuously secretes precisely at the growing tips of the hyphae as they approach the air interface.
Initially, when they are inside the wet substrate, these proteins are completely soluble in water.
But as they are pushed outward and reach the exact interface between liquid and air, they undergo a radical conformational change.
They spontaneously self-assemble into highly organized, rigid amphipathic films.
To visualize an amphipathic film, think of the way a drop of motor oil hits a puddle of water.
And instantly spreads out into that incredibly thin, iridescent, distinct layer.
It's a similar structural dynamic, but far more organized.
One side of the hydrophobin protein is hydrophilic.
It absolutely loves water and binds tightly to the wet cell wall.
The other side of the protein is fiercely hydrophobic.
It violently repels water and faces the open air.
By secreting these hydrophobins, the fungal hyphae essentially weave themselves a microscopic molecular raincoat.
Yes, the microscopic raincoat.
This film allows the delicate hyphae to physically break the surface tension of the water film they live in.
And forcefully push out into the open air without losing their internal moisture.
Without that hydrophobin raincoat, the hyphae would either be trapped underneath the surface tension of the water layer, unable to penetrate it,
or they would pierce it and dry out in seconds.
But with this amphipathic shield, they can confidently construct the incredibly complex, exposed aerial architecture of a fruiting body.
And what's remarkable is that we can actually witness the thermal footprint of this entire evaporation engine at work in real time.
We frequently use high-resolution, medical-grade thermal imaging cameras in our fruiting rooms.
Just to monitor substrate blocks without touching them?
When you look at a thriving, actively growing pin set through a thermal lens, the visual is stunning.
The young fruiting bodies are glowing in deep, cool blue and purple hues.
standing out starkly against the warmer orange and red heat signature of the metabolizing substrate block beneath them.
Our sensors confirm that actively evaporating primordia are consistently about 2.5 degrees Celsius cooler than their immediate surroundings.
That evaporative cooling is not a side effect. It is a vital, active protective mechanism.
The metabolic reactions required to build a complex mushroom at such a frenzied overnight pace are incredibly sensitive to heat.
If the internal temperature gets too high, the delicate metabolic enzymes required for cell wall expansion will literally cook and denature.
By constantly evaporating water off their surface, driven by that vapor pressure deficit, the young primordia maintain a highly precise, localized thermal microclimate.
That protects their enzymatic machinery.
If the ambient room temperature spikes too high, or worse, if the aphidation stops entirely because the air in the chamber becomes stagnant,
The internal temperature of the primordium spikes,
the enzymes fail.
and the pin aborts. It turns black, shrivels up, and dies.
This is exactly why the evaporation engine must be continuously maintained by the cultivator.
Which brings us to a significant practical challenge.
Evaporation is the engine of pinning.
It drives the hydraulic pull of water and nutrients, it concentrates the morphogenic signaling molecules, and it cools the sensitive enzymes.
But as cultivators, this puts us in a very tricky, precarious position.
How do we manipulate this biophysical engine to encourage maximum uniform pinning without accidentally driving it too hard?
And drying out the entire substrate block into a useless brick.
If we let it evaporate too fast, the mycelial network dies of acute dehydration.
If we don't let it evaporate enough, the engine stalls, the enzymes overheat, and we get zero pins.
To solve this thermodynamic puzzle, we have to master the application of water.
We have to master the art of the mist.
So we know evaporation is the engine, but there's a razor-thin line here for a cultivator.
How do you feed that engine without ruining the crop?
That's where the actual physical technique comes in, specifically the mechanics of misting.
Let's talk about microscopic dew versus heavy water.
Because this is where advanced biophysics meets daily practical cultivation technique.
The distinction here is critical. There's a fundamental biological difference between soaking a substrate surface and creating a microscopic dew.
Many novice cultivators, operating out of a misguided sense of care, make a catastrophic mistake here.
They aggressively spray their fruiting chambers with a standard, cheap household squirt bottle.
This deposits large, heavy macro droplets of liquid water that pool on the casing layer.
And sit directly on top of the delicate mycelial network.
From a biophysical standpoint, this is incredibly detrimental.
Heavy pooling water invites systemic disaster.
It physically suffocates the mycelium by blocking oxygen transfer.
It instantly halts the evaporation engine by eliminating the vapor pressure deficit at the surface.
And most dangerously, it serves as a perfect stagnant breeding ground for aggressive bacterial pathogens.
Bacterial blotch is the absolute nightmare scenario here.
Caused by the Pseudomonas bacteria.
If you leave heavy, stagnant water sitting on a developing mushroom cap or a primordium,
Pseudomonas will thrive in that localized puddle,
it rapidly multiplies and attacks the fungal tissue.
leaving ugly, slimy, dark brown or black lesions all over your harvest.
Completely ruins the crop and makes it unsellable and inedible.
The bacteria literally digests the mushroom while it's trying to grow.
To prevent this pathology, while still feeding the evaporation engine, we rely on the precise execution of the mist and fan protocol.
To replenish the moisture that is constantly being lost to evaporation without drowning the fungal network.
You must abandon the standard squirt bottle and use an ultrafine continuous aerosolizing mister.
Your goal is to generate a floating cloud of atomized moisture, not a localized rainstorm,
You aim the mister upward into the air above the substrate block.
allowing thousands of microscopic beads of water to gently drift down on the air currents and settle softly onto the surface.
When you do it correctly, it should look exactly like a delicate natural morning dew.
Just barely glistening under the gray lights, you shouldn't see puddles.
You should just see a shift in the way light reflects off the mycelium.
And a cardinal rule we enforce strictly in our lab: never ever spray growing primordia directly.
Once the pins have definitively formed and begun to elevate,
You miss the plastic walls of the chamber or you miss the air high above.
but you keep direct, heavy liquid water completely off the delicate developing fruit bodies.
They are too fragile, and their thermal regulation is too sensitive to be blasted with cold water.
The misting is only half of the thermodynamic equation.
Once you have applied that microscopic dew, you must immediately follow up with aggressive fanning for 30 to 60 seconds.
Fanning serves a vital dual purpose in this artificial environment.
First, as we discussed during the climate shift, it physically blows out the heavy pooling carbon dioxide,
which constantly sinks to the bottom of the growing chamber due to its molecular weight.
But second, and equally important for pinning, the forced air exchange forcefully strips away the saturated boundary layer of air sitting directly on the mycelium,
forcing the newly applied microscopic dew to begin evaporating immediately.
You are providing the moisture, and then you are actively mechanically vaporizing it.
This is how you continuously rev the evaporation engine without depleting the core block's water reserves.
You are artificially simulating the exact thermodynamic conditions of a humid, gentle breeze passing over a damp forest floor.
And here is a major trap that so many cultivators fall into, especially when they start relying too heavily on automated equipment.
They look at their digital hygrometer, they see it proudly reads 100% ambient humidity, and they think their job is done.
They think the environment is perfect.
But let me be absolutely clear. 100% humidity is not enough.
It is a profound misunderstanding of physics. You can have a chamber locked at 100% relative humidity and still have absolutely zero evaporation occurring.
If the air inside the chamber is completely stagnant,
remember, pinning does not require just the static presence of water.
It requires the dynamic movement of water from a liquid state on the cell wall to a gaseous state in the air.
If the air inside your tub is utterly still, the microscopic boundary layer of air directly hugging the mycelium quickly becomes fully saturated.
Once that boundary layer hits 100% saturation, the vapor pressure deficit drops to zero.
And the evaporation engine stalls out completely.
Which means the cooling stops, the hydraulic pull of nutrients stops, and the pinning stops.
You must have that gentle turbulence, that continuous air exchange, to continuously strip away that microscopic saturated boundary layer.
And keep the moisture moving. But what about passive systems?
Like perlite.
Right. A lot of growers use a thick layer of wet perlite at the bottom of their chambers.
They see massive condensation dripping down the walls of the plastic tub, and they assume, wow, it's incredibly humid in there, my mushrooms are perfectly hydrated.
But condensation can be incredibly deceiving.
Highly deceiving. It is crucial to understand the physics of temperature differentials.
Many cultivators equate wet walls with a wet substrate.
But condensation on the walls of a plastic fruiting chamber does not mean the mushrooms themselves are getting sufficient moisture.
Condensation is purely a thermodynamic function of temperature differentials.
It is simple physics. Condensation will always form on the warm side of a barrier when the other side is cooler.
Exactly. If your general grow room is kept at a comfortable 68 degrees Fahrenheit.
But the biological metabolic heat generated by a massive block of colonizing mycelium inside the closed chamber raises the internal air temperature to 72 degrees.
The moisture in that trapped air will inevitably condense onto the inside of the cooler plastic walls.
I try to explain this to our techs with a simple analogy.
Let's hear it.
I've had a freezing cold can of soda build up massive, dripping condensation sitting on a picnic table in the bone-dry heat of an Arizona summer.
That condensation had absolutely nothing to do with the Arizona air being at 95% humidity.
It was purely the extreme temperature differential between the liquid inside the can and the air outside.
So as a cultivator, do not let dripping condensation fool you into thinking you don't need to mist or monitor your substrate.
You still have to monitor the actual physical surface of the mycelial block.
Furthermore, to truly hydrate a substrate, surface misting is often completely insufficient.
Especially after a massive first flush of mushrooms has severely depleted the internal water reserves of the block.
You cannot simply mist the surface and expect that water to penetrate 3 inches deep into a dense, hydrophobic brick of mycelium.
This is where we rely on a much more aggressive hydration technique known as dunking and rolling.
In our lab protocols, after a fully colonized grain or sawdust cake has produced its first harvest,
we remove it and submerge the entire block completely underwater for 12 to 24 hours.
Now, why does dunking work so much better than heavy misting?
Because dunking relies on the fundamental biological and physical principle of osmosis.
By physically pushing the cake underwater. And we usually put a heavy, sterile glass plate on top of the cakes to keep them fully submerged because they are so buoyant they will try to float.
We apply constant hydrostatic pressure to the exterior of the block.
This sustained pressure literally forces water molecules to migrate across the semi-permeable membranes of the billions of individual mycelial cells deep within the core.
It vastly outperforms surface misting for deep systemic hydration.
Misting only treats the superficial surface layer.
But dunking physically inflates the billions of dehydrated cells deep inside the structural core of the block.
Once those cells have soaked up all that water through osmosis and returned to maximum turgidity,
We remove them from the water, often roll them in dry vermiculite to create a fresh, moisture-retaining microporous casing layer.
and place them back into the fruiting chamber.
But, and this is a mouthful, remember the physics of the boundary layer.
Once those soaking white blocks are back in the chamber, you must immediately resume the active mist and fan protocol.
I remember vividly, early in our career, we lost an entire batch of beautiful, promising pins on second flesh cakes.
We soaked the cakes, put them back into a sealed still air chamber, and went home for the weekend.
We thought, they have plenty of water, they'll be fine.
Have them soaking wet in totally stagnant air.
Because there was no airflow, the evaporation engine couldn't start.
The boundary layer saturated instantly,
The Pseudomonas bacteria had an absolute field day in that stagnant moisture.
and by Monday morning, every single pin had aborted, turned into a black rotting speck, and smelled awful.
It was an expensive, harsh lesson in the absolute necessity of maintaining air movement.
It is a relentless, delicate balance.
You must provide the water, but you must simultaneously provide the physical mechanism for its evaporation.
So let's assume the misting and fanning are dialed in perfectly.
The evaporation engine is humming along.
The morphogens are concentrated, the hydrophobins are doing their job, and the hyphal knots begin to form.
You start seeing these dense, bright white clusters appearing across the surface of the substrate.
But how do these microscopic, dense knots inflate into massive, fleshy, heavy mushrooms, sometimes seemingly overnight?
To understand that explosive growth, we have to examine the profound biophysics of cellular pressure,
This is hands down one of my absolute favorite topics in mycology.
because it challenges everything about how we normally think about biological growth.
When a plant or an animal grows, it's primarily doing it through the slow, methodical process of cell division.
One cell splits into two, two split into four.
And the organism slowly adds biomass and gets bigger over weeks or years.
But a mushroom is an entirely different biological machine.
A mature mushroom is over 90% water.
It's explosive. Overnight growth, where a pin can quadruple in size in 24 hours, is not primarily driven by the slow process of cell division.
The actual cells that make up a mushroom are already fully formed during the microscopic primordium stage.
They are just incredibly tiny and tightly packed together, like an uninflated parachute.
The explosive growth of the fruiting body is driven almost entirely by rapid cellular expansion.
And the sheer fuel for that expansion is liquid water.
The precise mechanical physical force at work here is known as Turgor pressure.
Turgor is the internal hydrostatic pressure that pushes the plasma membrane of the fungal cell forcefully outward against its rigid, chitinous cell wall.
It is the exact same hydraulic force that makes a wilted, drooping houseplant suddenly stand up stiff and straight a few hours after you water it.
But in fungi, this hydraulic system is turbocharged to an unimaginable degree.
To inflate these millions of cells so rapidly and simultaneously, the fungus utilizes a highly sophisticated, rapid response biochemical pathway.
Known as the osmotic mitogen-activated protein kinase cascade, or the MAPK cascade.
Let's translate the MAPK cascade into what's actually happening on the factory floor inside the cell.
The mycelium spent weeks during the colonization phase, silently storing up massive amounts of potential energy in the form of complex carbohydrates.
Specifically large molecules like glycogen.
Suddenly, the environmental signals, the evaporation, the cold shock, the light, they trigger the MAPK cascade.
This flips a genetic switch, and the fungus, rapidly, almost violently, begins breaking down that massive inert glycogen reserve
Into highly concentrated, simple, soluble sugars, specifically mannitol and trehalose.
The creation of those simple sugars is the key to the hydraulic pump.
Because the concentration of these dissolved sugars inside the hyphal cells suddenly skyrockets.
A massive osmotic gradient is created between the inside of the cell and the surrounding environment.
The inside of the cell is now incredibly dense with solutes compared to the relatively dilute water in the substrate outside.
And the fundamental laws of thermodynamics and physics dictate that water will always rush across a semi-permeable membrane to balance an osmotic gradient.
Nature abhors that imbalance.
So water is violently rapidly drawn from the damp substrate.
Pulled through the cell walls and forced into the hyphal cells.
It inflates them precisely like microscopic water balloons attaching to a high-pressure hose.
But it isn't just a localized inflation at the base.
Because aqueous fluids like water and cytoplasm are physically incompressible.
The physics of this massive water uptake at the base and center of the mycelial network creates an astonishing physiological phenomenon.
Known as the mass flow of cytoplasm.
The sheer volume of water rushing into the core of the network has nowhere to go but out.
Seeking the path of least resistance, which is toward the expanding tips at the periphery. Up into the growing mushroom.
This mass flow builds incredible localized internal pressure.
It forces not just the water, but the entire cytoplasm, which is packed with vital organelles, synthesized proteins, enzymes, and structural building materials,
to stream forward through the network at incredibly high speeds.
rushing directly into the expanding tissue of the fruiting body.
It is essentially a microscopic, organism-wide fire hose.
But wait, if there's all this cytoplasm and water rushing through, how does the cell membrane manage that flow without rupturing?
To handle this massive, high-speed flow of liquid across the vast fungal network, the fungal cell membranes are heavily embedded with highly specialized protein channels.
Called aquaporins.
Aquaporins are essentially microscopic, high-efficiency plumbing fixtures that act as selective turnstiles.
They only allow single water molecules to pass through in a rapid single-file line, blocking larger ions or molecules.
They facilitate this incredibly rapid, highly controlled transport of pure water from the damp substrate deep below.
Straight up the elongating stem and into the expanding tissue of the cap.
The sheer physics of this transport mechanism is staggering.
And if you want to understand just how powerful this hydraulic system is in practical terms, you only have to look at what mushrooms are capable of achieving in the real world.
Have you ever been walking and seen a delicate-looking ink cap mushroom literally push its way through solid paved asphalt in a parking lot?
Yes, or lift heavy, packed debris like a thick layer of crushed gravel or a heavy paving stone.
It looks impossible.
You have a fleshy organism that you can easily crush between your fingers, yet it's shattering concrete.
The structural immensity of the pressure generated by these microscopic water pumps is mind-boggling.
When we measure it in the lab, we are talking about localized Turgor pressures that can easily exceed 100 pounds per square inch at the apex of the hyphal tip.
To put that in perspective, that's significantly higher pressure than the air inside a standard car tire.
The mushroom is quite literally hydraulically jacking itself out of the ground using the incompressible nature of water.
It is biological hydraulics at its finest.
And as this immense Turgor pressure forces the stem to rapidly elongate and forces the cap to expand outward and upward like a slow-motion opening umbrella,
It sets the stage for the final, ultimate act of fungal reproduction.
the entire organism's life cycle culminates in the micromechanics occurring underneath the cap.
Let's paint a detailed visual picture of what is happening on the gills during this final expansion phase.
The gills are the true biological factory of the mushroom.
As the cap expands outward, driven by Turgor pressure, the delicate gills underneath begin to unfurl and align themselves perfectly vertically.
And on the microscopic surface of these gills, millions of highly specialized reproductive cells called basidia are developing.
If you look at them under a high-powered electron microscope, they look like a dense forest of tiny clubs or cobblestones lining the steep walls of the gills.
Inside each and every basidium, the ultimate genetic event of the organism's life takes place. Karyogamy.
Karyogamy is the fusing of genetic material,
Remember, up until this point, the mycelium has been eukaryotic.
meaning it contains two distinct unfused nuclei in every cell, inherited from the two original spores that mated months ago.
In the basidium, those two distinct nuclei finally, permanently fuse together into a single diploid nucleus.
And immediately after fusing, they undergo meiosis,
A rapid sequence of cellular division.
splitting apart to form 4 brand new, genetically unique haploid spores.
And the release mechanism for these 4 spores is another absolute marvel of biophysics.
The spores are perched precariously on tiny microscopic stalks at the very end of the club-shaped basidium.
A microscopic droplet of water, known in mycology as Buller's drop, begins to slowly condense at the base of each spore.
As this spherical drop of water grows larger by pulling moisture from the highly humid air between the
It
gills.
eventually touches and merges with a separate, incredibly thin film of water coating the spore's surface.
The physics of that merger is explosive.
When those two water surfaces connect, the sudden, violent shift in the center of mass and the rapid equalization of surface tension creates a localized, momentary release of kinetic energy.
It is essentially a microscopic gas bubble-driven explosion.
This physical reaction forcibly catapults the spore off its stalk and away from the basidium.
The acceleration is beyond comprehension. The spore is launched at an acceleration exceeding 10,000 Gs.
10,000 Gs, that makes it one of the fastest documented movements in the entire biological kingdom.
And it's powered entirely by the simple physics of water condensation and surface tension.
And it launches the spore exactly far enough to clear the microscopic structures of the gills before gravity catches it.
Allowing it to drop smoothly downward and drift away on the ambient air currents.
It's perfect microballistics.
But wait, we skipped a crucial overarching navigational step.
We've built this massive hydraulic mushroom using the evaporation engine. We've inflated it using the massive force of Turgor pressure, and we've successfully ejected the spores.
But how does this completely blind subterranean organism know which way is up?
How does it guide this immense hydraulic machine so that the spores fall perfectly downward out of the gills instead of smashing directly into the dirt or the side of the tub?
That navigational mystery brings us to our final major topic: directing the harvest.
We have to look at the roles of light, gravity, and final environmental tweaks.
While evaporation and fresh air act as the metabolic engine and the physical building blocks of the mushroom,
Light and gravity serve as its sophisticated, highly sensitive navigation system.
let's clarify the role of light first, because it is probably the single most widely misunderstood concept in amateur cultivation circles.
Many people think mushrooms need light to grow in the same way plants need light for photosynthesis.
Right. But fungi don't photosynthesize. They don't generate energy from light.
Light is strictly a secondary pinning trigger and a navigational beacon.
It is vastly overrated as a primary fruiting trigger compared to the absolute critical importance of maintaining evaporation and managing CO2 reduction.
In fact, if you manage your air exchange and evaporation perfectly, you can actually fruit many species of mushrooms in complete pitch black darkness.
However, if you want them to look normal and drop spores efficiently, light is highly necessary for orientation.
This process is known as phototropism.
Phototropism is the biological imperative to grow toward the light.
When the primordium is very young, just a tiny knot of tissue, it is heavily positively phototropic.
It desperately wants to find the open sky.
And it achieves this using a highly sensitive molecular photoreceptor complex embedded in its cells known as the white collar complex, or the WCC.
The WCC is specifically chemically tuned to detect high-frequency blue light.
It sits dormant in the fungal cells, and when blue light photons penetrate the cell and strike it, it activates a transcription factor complex.
This alters the localized growth patterns of the cells, causing the cells on the dark side of the pin to elongate faster.
Which causes the young pin to physically bend and grow toward the strongest source of blue light.
It's essentially using the light to calculate the shortest, most direct path out of the dark soil or leaf litter.
But hold on, if it's tracking blue light, why do so many older grow guides recommend standard warm red incandescent bulbs?
Honestly, they shouldn't. As the mushroom matures and the cap begins to fully expand, a fascinating biological shift occurs.
The primary navigation system actively switches off the phototropism and hands control over to negative gravitropism,
The mushroom stops caring almost entirely about where the light source is in the room.
and becomes fiercely, single-mindedly dedicated to growing strictly upward, directly against the pull of gravity.
The structural precision required here is non-negotiable,
The stem elongates perfectly vertically, like a plumb line.
while the cap simultaneously levels out so that the gills face absolutely perfectly downward toward the earth.
If the cap is tilted or the gills are angled even a few degrees off axis, the spores being shot off the basidia at 10,000 Gs will simply crash into the opposite gill wall.
And become permanently trapped.
If that happens, the entire massive reproductive effort, all that energy and hydraulic pressure, is rendered completely useless.
The organism fails.
But I've always wondered about the actual mechanics of this. How does a fungus, essentially a bag of water and chitin, feel gravity.
It doesn't have an inner ear with fluid and tiny hairs like we do to maintain balance.
The leading biophysical theory, which is backed up by some incredibly cool clinostat experiments and even some experiments flown in zero gravity on the space shuttle,
Involves complex calcium gradients and the cellular cytoskeleton.
the micromechanics of sensing gravity are brilliant.
The cells in the rapidly growing, elongating zone of the mushroom stem utilize a dense, complex internal network of cytoskeletal microfilaments.
It is widely believed that heavy, dense organelles within the cell, possibly the large nuclei themselves, act as microscopic biological weights, or statoliths.
As these heavy organelles naturally sink and pull down on the delicate microfilaments under the constant force of Earth's gravity.
They trigger localized calcium ion-mediated signal transduction pathways.
It's a highly localized, autocorrecting biochemical cascade.
If the mushroom stem starts to lean slightly to the left, the cells on the lower side of that leaning stem detect the heavier, sustained pull of those organelles.
The resulting calcium signaling tells those specific localized cells on the bottom curve to rapidly take in more water and elongate faster.
Which physically jacks the stem back up to a perfect vertical alignment.
The mushroom is constantly micro-adjusting its hydraulic pressure to stay perfectly upright.
And the precision of these environmental sensors extends far beyond just spatial orientation.
Consider the broader systemic role of the WCC, the blue light receptor we discussed earlier.
The WCC is not just a simple directional sensor pointing toward the sun.
It functions as the central regulating gear of the organism's entire fungal circadian clock.
The circadian clock mechanism blows my mind every single time.
The fungus isn't just mindlessly reacting to the light switching on and off in the room.
It is actively internally keeping time.
By detecting the daily cycles of light and dark, the circadian clock regulates the organism's internal metabolism.
So that the final maturation of the basidia and the explosive release of the spores is meticulously timed to coincide perfectly with the early morning hours.
The evolutionary reasoning for this timing is rooted entirely in survival thermodynamics.
Why early morning? Because early morning is when ambient atmospheric humidity is at its absolute highest.
And disruptive wind speeds are generally at their lowest.
If the fungus were to release its microscopic, delicate, water-dependent spores into the blazing heat and dry air of the midday sun,
they would instantly desiccate, die, and become non-viable before they ever hit the ground.
by chemically syncing its reproductive cycle to the planetary rotation and thermal cycles.
The WCC ensures the spores are released directly into the cool, damp, protective morning dew,
giving them the maximum possible chance of survival.
It is a remarkable, elegant integration of biophysics, genetics, and extreme environmental awareness.
And this brings us right back to the practical realities of the laboratory and your own cultivation grow room.
Armed with this deep understanding of the physics, you can stop guessing and start optimizing your environmental tweaks.
For instance, knowing definitively that the WCC photoreceptor is specifically activated by blue light photons, we completely adapt our lighting systems.
In our lab, we consistently find that providing higher frequency light, anything above 5,000 Kelvin, which sits much closer to the blue spectrum,
Produces far superior, more dense, and much better oriented pin sets than standard incandescent bulbs.
which are heavy in the useless red spectrum.
The WCC simply doesn't see red light effectively enough to trigger a strong response.
Exactly. Ditch the warm white bulbs and invest in crisp, cool daylight LEDs.
But beyond the hardware and the equipment, the absolute most important lesson here is about developing your intuition as a cultivator.
You have to move beyond rigid, inflexible schedules.
Do not water your substrate just because it's Tuesday and a chart told you to.
You have to learn to trust your tactile senses and your active observation.
If you want to know if your bulk substrate needs water, don't just stare at a digital humidity gauge on the wall.
Open the tub, reach in, and physically pick up the substrate block.
Yes, judge its moisture by its actual physical mass.
A fully hydrated, healthy block is dense and surprisingly heavy.
A severely depleted, dehydrated block feels light, almost like styrofoam, and sounds hollow when you tap it.
Look closely at the surface for that glistening microscopic dew we talked about.
Watch the behavior of the stems for the earliest signs of CO2 legging.
You have to actively observe the living organism and react dynamically to what its biophysics are telling you.
Rather than trying to force it into a static spreadsheet.
Observation over rigid rules. That is the true hallmark of a master cultivator.
You are managing a highly dynamic, living, breathing system that is constantly sampling and reacting to its environment.
Through the physics of evaporation, the hydraulic pressure of water, and the subtle gradients of light and gravity.
So we've taken you on quite a journey today.
We've gone from the dark, high CO2 suppression of the underground spring,
Forced our way through the violent biophysical climate shift of the evaporation engine.
navigated the razor-thin line of microscopic dew,
Built a massive high-pressure hydraulic machine out of pure water.
and finally, guided it precisely to the harvest using light receptors and gravity-sensing satellites.
But before we let you get back to your lab and your grow room, we want to leave you with a final, slightly mind-bending concept to ponder while you work.
Think deeply about the sheer, overwhelming sensitivity of the sensory systems we have discussed today.
The hygroscopic, hyphae mapping, microscopic vapor pressure deficits in the air.
The WCC detecting precise nanometer frequencies of light.
The continuous molecular level sampling of CO2 concentrations.
Now, consider the thermodynamic reality of what happens when you physically walk into your climate-controlled grow room to check on your crop.
It's wild to think about. You walk in, the mere act of the door opening violently shifts the air currents.
Instantly altering those delicate microclimate boundary layers sitting on your casing soil.
The infrared heat radiating from your physical body subtly changes the local temperature gradients in the room.
But most profoundly, you breathe.
Every single exhalation you make releases a massive, dense spike of carbon dioxide directly into the room's atmosphere.
The mycelial network is so exquisitely tuned to its environment that it is undoubtedly detecting these shifts the second you cross the threshold.
It is sensing the sudden drop in vapopressure as the air moves around your body.
It is registering the distinct spike in CO2 from your breath.
You are not just an impartial, disconnected observer standing outside a glass box looking in at an experiment.
The exact moment you enter that room, your physiological presence fundamentally alters the thermodynamic and biochemical equations happening on the surface of the substrate.
You are actively, physically becoming part of its complex environmental trigger system.
You aren't just watching the physics of the room.
You are the physics of the room. The fungus knows you are there.
It is a humbling and profound reminder of the deep, physical interconnectedness of biological life.
Thanks for listening, happy growing, and don't forget to subscribe.